So as we dig deeper into blood pressure in this video, this is a slide that we saw yesterday, again trying to kind of bring everything full circle. So we can lump these two in, again, heart rate and stroke volume, and we already know that cardiac output goes up, right? We just talked about that supply and demand, that we supply more blood by pumping more blood as an increase in stroke volume per beat, and also increasing the number of beats. We can also say that blood volume and blood viscosity, for all intents and purposes, don't really have any effect during exercise. There maybe is a little bit of viscosity increase if you get very dehydrated or if you drink a lot of water, but for the most part, your blood volume and your blood viscosity both stay exactly the same when you start to exercise, right? So cardiac output goes up. What happens to peripheral resistance, right? So does it increase? Does it decrease? What happens? Let's talk about it. So just as a reminder, we'll talk about that there are some broad laws governing blood flow. Blood flow, again, goes from high pressure to low pressure, and the rate of flow is proportional to the pressure difference at the two ends. If we think about this on a global scale, I talked about this last time, that we have this really high pressure heart and the low pressure veins, and so we get a large amount of flow, right? But we can also adjust that pressure difference based on opening and closing vessels, which will be the next part, right? And so ultimately, blood flow is equal to the change in pressure divided by resistance. And as we mentioned yesterday, altering the radius of the vessel is the most important part. You'll remember that it's the radius to the power of 4. So altering the radius has a massive impact on that. And indeed, the body has really great ways at being able to do that. So one thing we can do is we can vasodilate and vasoconstrict our arteries and veins. Right? So here's our arteriole in this case. Our arteriole has nicely drawn here smooth muscle. It's muscle cells, which means it has the ability to contract. They're different than skeletal muscle, but the same concept. They use actin and myosin to contract and relax, and able to either dilate, which is relaxing, or contract, which is vasoconstricting, right? So we have that ability, and then we also have the ability to regulate blood flow. So one of the ideas is that we have these precapillary sphincters. What these sphincters do is they act just like any other sphincter that you may have learned about in physiology, is they're essentially a valve that can open and close. Right? So if we open the sphincter, then blood flow is allowed to come in. If we close the sphincter, then we allow minimal blood flow in that. So these are located right below capillaries, and these are very important because we don't have capillaries, we don't have every single capillary open in the body at all points in time, right? And if we look at what it actually looks like, we actually are able to alter blood flow at rest and during exercise by opening and closing these sphincters, right? So if we look at blood flow at rest here, which is in the top, you'll see that about 5% of blood flow goes to bone. We get a pretty healthy chunk of it to brain. Heart gets its own. Liver and kidneys get quite a bit, right? Liver is for metabolism, providing glucose, and kidney is an important filter. We send 7% or so to the skin, and our muscles get a pretty healthy chunk, right? They still demand a lot of oxygen. As we start to exercise, what happens is we shift most of this blood from our non-necessary regions, like our liver and our kidneys, and we send as much blood flow as we can. So at rest, anywhere between 15 to 20% of cardiac output to skeletal muscle. During maximal exercise, it can be 85. This figure here is 87% going to muscle. In order to do that, we have to decrease blood flow to less active organs. We can do that by several ways, but the major way is by vasoconstriction and opening up the sphincters in the skeletal muscles in order to do that. So let's take a look at another way that we can look at this blood flow. So again, at rest and at exercise, I'll point out a couple things. At rest, cardiac output, you'll remember, is about 5 liters per minute. At heavy exercise, here this is slightly larger than that first calculation, but it's about 25 liters per minute. So I have several things highlighted already in this. So first you'll see the heart. The heart actually requires a large amount of blood. It's a contracting organ. That metabolic demand is therefore high, and so we must meet that metabolic supply. As we exercise, what happens to heart? It has more contractions, the heart beats faster, metabolic demand goes up. Right? But if you look at it, the percentage of blood flow that it's getting out of 100 stays the same. But if you take about 5% of 25 liters, that's much greater than 5% of this 5 liters. So therefore, we can say the heart doesn't get an increase, it doesn't get its increased blood flow from redistribution. Instead, it just gets its increase in blood flow from an increase in cardiac output. Another important one is the brain. You can see here, percentage-wise, the brain actually goes down, right? But brain blood flow is very tightly regulated. We don't want it to go down. If it goes down, you pass out. If it goes up, you have an increase in intracranial pressure, which can cause brain hemorrhaging and be bad. So you'll see that the brain will actually get a decrease in flow percentage-wise, but maintains the approximate exact amount. And then again, if we look at skeletal muscle, 15 to 20%, it's about 0.75 liters. At exercise, we get almost all of it, 20%. So here is an interesting conundrum. So we've talked about sympathetic nervous system activity going up several times throughout the last couple of lectures. So what is sympathetic nervous system doing in this? So sympathetic nervous system is actually regulating a large part of this. So in many of our regions that have reduced blood flow, the sympathetic nervous system is actually causing constriction. So that's right, our sympathetic nervous system is actually inhibiting blood flow to specific areas, right? It's causing constriction. So that doesn't make sense, does it? If you're thinking about this, how do we have sympathetic nervous system causing constriction, yet muscle blood flow goes drastically up? So here is what is, I think, a really cool idea in physiology. It's not really well explained, but we know what happens. So blood flow to organs is, again, caused by, is regulated by the sympathetic nervous system. So increase in epinephrine and norepinephrine will cause constriction. However, organs, specifically skeletal muscle, have their own ability to regulate blood flow based on their metabolic needs, and that principle is called autoregulation, which is pretty interesting. So you may say, how does autoregulation work, right? Again, vascular resistance goes up due to sympathetic stimulation. So how do we then do that? Local metabolites. And if you think about this, these are things that in exercise are going to go up, right? So we're going to produce CO2, which we learned about as we break down glucose. We'll release potassium from all the skeletal muscle contractions being released. We'll, of course, have a change in pH. We'll release adenosine from ATP. And so you'll see that a lot of these, when they are released from the muscle, they go to very nearby arterioles, causing them to relax, therefore decreasing vascular resistance and increasing blood flow. So that's pretty amazing. We had this system where we cause all the skeletal muscle arteries to kind of constrict via sympathetic nervous system, and then the ones that really need it based on their metabolism, we use those products of metabolism to then cause dilation to get more blood flow there, right? We combine that with recruitment of capillaries, so at rest 50 to 80% of them are open, but during exercise almost all are open. So as you can imagine, this effect, because the skeletal muscle is such a large organ, right? So it's such a large mass that ultimately total peripheral vascular resistance is actually going to go down during exercise because of all the vessels that are being opened due to this autoregulation. So then, if we look at what happens to blood pressure to close out the lecture, we'll actually have two options, or we'll talk about two cases. So one, we'll talk about dynamic, which is again running, and we'll talk about static, which is resistance training. So this is these are the two differences. Again, when we look at what blood pressure is going to need, we're going to need for running, as we've already seen, increased cardiac output, increased heart rate, a decrease in total peripheral vascular resistance, as we just explained. Diastolic blood pressure is going to stay the same. What happens to systolic blood pressure? It increases. We'll see these in the next figure. Static exercise, resistance exercise, we need increased cardiac output. We need an increase in heart rate. However, we get an increase in total vascular resistance. So here's the difference in the two. This is because while these metabolites are being pushed, that same muscle pump that was really benefiting in this dynamic exercise is causing us problems in our static exercise. When you do a static resistance exercise, what you do is you contract that skeletal muscle, which ultimately squeezes down on the vessels, on the arteries, on all the veins, and what it does is it causes blood pressure to shoot up because you have blood flow trying to be pressed through, especially in the arteries, but it's not allowed to press through because that artery is blocked off due to the contraction of the skeletal muscle. Therefore, total peripheral vascular resistance goes up and it has an effect on blood pressure. So ultimately we'll see, here's what blood pressure looks like during exercise. So in dynamic exercise or dynamic, our diastolic blood pressure or our relaxation pressure stays about the same. In normal, that is 80 millimeters of mercury. Our systolic, we'll stick with our dynamic exercise, is it increases linearly, and you'll see the duration, so this is not intensity, this is duration. As the duration gets very long, what happens is we actually start to see a decrease in systolic blood pressure due to a lot of blood flow actually going to the skin and total peripheral vascular resistance going even further in order to regulate body temperature usually. But for the most part, what we see is a linear increase in systolic blood pressure, no change in diastolic blood pressure during dynamic running, cycling, where you're moving. In static, we see an increase, same increase in systolic blood pressure relative. However, at maximal, it gets to a much, much higher level. Indeed, it's not uncommon to get 330 millimeters of mercury here, whereas dynamic is usually 220 or so. Okay. Also, because total peripheral vascular resistance is much higher, diastolic blood pressure also increases linearly with that. So as you can imagine, these are going to have big impacts, maybe a suggestion to avoid static exercises if you have someone with high blood pressure. We'll finish up this module with a look at not only the idea that we are delivering more blood, which is delivering more oxygen to muscle for contractions, But the last concept is that we also extract more oxygen during exercise from the blood. So what we look at is what's called the arteriovenous difference, or AVO2 difference. It represents the amount of blood that's taken up from approximately 100 mils of blood. When we measure this, usually what we do is we measure the arterial concentration coming from the heart, and then the venous side coming near when it is returned to the heart, to see how much of oxygen is actually taken up with that. So it's not looking at specific tissues, it's looking at whole body overall. So as you can imagine, as we get more metabolically active, that AVO2 difference is going to increase over time. Okay? And we see that. So once what we see is as exercise intensity increases, we actually have an increase in AVO2 difference. We extract more oxygen out of the blood. And then at about 50%, we just see that it levels off and doesn't extract near as much. What we can do is we can then use this based on our ability to solve metabolic supply and demand, is our oxygen consumption is going to be equal to the amount of blood that we send, cardiac output, multiplied by the amount of oxygen we take out of that blood, which will ultimately tell us how much oxygen we can consume, and therefore our metabolic demand is here and our metabolic supply is here in this equation.